In the previous section, we had discussed about the Gaussian elimination process and what is the end objective in the Gaussian elimination process, where we convert the augmented matrix representing the set of equations into another matrix called as the row-echelon matrix. Today we will see what are the steps or the operations that we need to perform in converting the augmented matrix into the row-echelon form of the matrix. In the row-echelon form of the matrix, the elements below the diagonal, so if this is the diagonal of the A matrix, which is the coefficient matrix, all the elements below this diagonal, that is these elements, are converted or transformed into 0 by performing certain row operations. So what we want to do is to perform some operations on the rows and make these elements which are below the diagonal as 0. And to do that, the procedure that we have to follow is as follows. So we will use what we call as the pivots, and if you recall from the previous section, the pivots are the elements or the numbers which lie along the diagonal of the coefficient matrix. So the pivot for the first column is the number present in this position. The pivot for the second column is the number present here, which is along the diagonal, and the pivot for the third column is here. So the pivots are the elements or numbers which are present on the diagonal of the coefficient matrix. And what we want to do is we want to perform certain row operations using these pivots. For example, in the first step, we want to make this 4 and this 1 over here into 0. Whatever is the value of these numbers, we want to perform some operation on these numbers and transform them into 0. Similarly, we want to perform some operation on this number and transform into 0. And when we are performing converting these numbers into 0, the pivot for these numbers in the first column will be the element in the top left position of the first column. So using this element as our pivot, we will transform these numbers into 0 by performing certain row operations. But whatever calculations we apply to convert this 4 to 1, we have to apply it to the entire row, so that the relationship between the variables is still maintained. So the row operation will be applied to the entire row 2 and row 3 using this number as the pivot, so that these two numbers will be made as 0. And then in the subsequent step, we will move on to this position, and using the value that is available after the first step over here as our pivot, we will transform this number, whatever it is in the subsequent step, we will transform that into 0. And to do that, because this is in row 3, we have to apply that same operation to the entire of row 3. So we'll have to apply the transformations to the entire rows, not just to the specific number that we want to transform. And whenever we are transforming these numbers, we have that we will use the element on the diagonal as the pivot, and for the first column, the top left element will be our pivot. For the second column, the element on the diagonal here, that becomes our pivot, and so on. So the objective is to convert the augmented matrix into the row echelon matrix. So let me also write down what are these numbers, these positions, not the numbers specifically, these positions which I am marking in green, they are called as the pivots. So these are the pivots, and at the end of this, we will have a matrix which has these numbers in the lower triangle as zeros. All these will be transformed to some other values. In fact, the first row will not get transformed at all. It will have the same numbers, 1, -1, 3, and 5. Row 2 will get transformed to some other numbers, and similarly row 3 will get transformed to some other numbers, right? But these elements in the below the diagonal, they will all get converted to 0. We call this form of the matrix as the row echelon matrix. Okay, and once we convert the augmented matrix into the row echelon form, we can solve for the equations and get the values of the variables. Let us also label the rows as R1, R2 and R3. So we have in this case 3 equations, so we have 3 rows. So the first row we will call it as R1, the second row we call it as R2, and the third row we are going to denote that as R3. So we are going to represent each of these rows as R1, R2 and R3 respectively. Now let us see what is the process involved in converting or transforming this augmented matrix into the row echelon form. So in the first step, we are going to convert these 2 elements into 0 by using this position as our pivot. So the green green square represents the pivot position, and the red rectangle which I marked or circled around the numbers, those numbers represent the values that we want to convert to 0. We want to transform them to 0. So the 4 here is in row 2. So whatever calculation we do to convert this 4 into 0, we have to apply the same calculation to the entire of row 2. Similarly, whatever calculation we do to convert this 1 into 0, that same calculation has to be applied to the entire row 3. So we will see what is the procedure. There are many ways of doing it, but I will show you one of the easier methods that would also allow you to do it in a simple way and also avoid any repeat calculations. Okay, so if you follow this procedure, you will not end up changing any previously converted values that would make you to have to convert them back to 0. Okay, so you will see what I mean by that. So the first step is we want to convert this 4 into 0 using the 1 on the top here as the pivot. So the 4 is in row 2, so we have to make some operation or some transformation to row 2. So the transformation that we are going to apply here is something like this. So I'll write it as row 2, which is R2, transforms into R2 minus, this is the standard procedure, we'll write it as R2 becomes R2 minus whatever number that we want to make as 0. We want to make this 4 as 0, so we'll write that 4 divided by whatever is the number present in the pivot position. So the pivot position here has the number 1, so we'll say divided by 1. And where is the pivot position? The pivot position is in row 1. So the pivot element in this particular case is present in row 1, so we'll say we'll multiply it by row 1. So this will be the transformation that we apply to all the elements of row 2. So we can write that as R2 minus 4 by 1 is 4, R1. We have to apply this transformation to each element of row 2. So R2 will become R2 minus 4 R1. So that's our transformation. R2 becomes R2 minus 4 R1. So the first row is going to remain as it is in our next step. So we'll write that as it is. So 1 minus 1, 3, 5. The first row is as it is. The second row is going to change because we are applying this transformation to the second row. And we have to do it for each element of the second row. So we have to apply it to this 4. So in the second row, we have the first number as 4 minus 4. And the corresponding element in R1 is 1. So into 1. So that becomes 0. So we'll write that number here. For the second element of row 2, the number that is present here is 2. So we'll write that 2. So in place of R2, we are writing that 2 minus 4. And in place of R1, we have to write the corresponding number in R1. So here, the corresponding number in R1 is minus 1. So minus 4 into minus 1, so that will become 2 plus 4, which is 6. So that becomes equal to 6. So we'll write that 6 over here. And then the third number in this row 2 is minus 1, and the corresponding number in row 1 is 3. So in place of R2, we'll put minus 1, and in place of R1 here, we'll put the 3. So that will become minus 1 minus 4 times 3. That will become minus 13. So we'll put, in place of minus 1, we'll replace it by the transformed number, which is minus 13. And similarly, for the fourth number here is in R2 is 0, and the corresponding number in R1 is 5. So in place of R2, we'll put the 0, and in place of this R1, we'll put this 5. So that will become 0 minus 4 times 5, which is equal to minus 20. So this becomes minus 20. So R2 has been transformed according to this rule. And the way to write the rule is R2 transforms to R2 minus whatever number is present here. In this case, the number present here is 4. So we have written 4. Divided by the pivot. In the pivot position, whatever is the value that is present here. In this case, it's 1. So we put 1. If this was 3, we'll put 4 by 3. If this was, for example, if the number here in place of 4 was 5, the numerator will be 5. So whatever is the value present here, that goes in the numerator, and whatever is the value present in the pivot position, that goes in the denominator, and then we multiply with the row where the pivot is present. So the pivot is present here in row 1, so we put R1 here. So that's the rule we are going to follow in writing the row operation or the transformation that is going to be applied to transform the rows into so that we get the row echelon form of the matrix. Now we have to apply a similar transformation to row 3. So what would that be? Row 3 will transform to R3 minus, it is this number that we want to make as 0. So the value of the number present here in this case is 1. So we'll put that 1. And the pivot number is also 1. So it will become 1 by 1. And where is the pivot position? It's in row 1. So 1 by 1 into R1. If this was 2, we'll put 2. So in this case, it's 1. So we'll just put it as 1 divided by the pivot. The pivot value here is 1. So divided by the pivot, 1 by 1. And where is the pivot? The pivot is in R1. So the pivot value in this case is present in R1. So when we are converting the numbers in the first column, okay, below the diagonal to 0, we'll have to use this top number in the first column as our pivot. And when we come to the second column, this position will become the pivot. When we come to the third column, this position becomes the pivot, and so on. Okay, so in this case, for R3, we want to make this number as 0. It's in R3. So we want to make a transformation to R3 or row 3. And the transformation is R3 minus the value that is present here, which is 1, divided by the pivot. The pivot value is 1, and the pivot is present in row 1. So simplifying this equation, it simply becomes R3 transforms to R3 minus R1. So all we have to do is, in place of R3, we have to put R3 minus R1. So the number present in R3, the first element in R3 is 1, and the corresponding first element in row 1 is 1. So 1 minus 1 will give us 0. So the first calculation is 1 minus 1 equals 0. And the corresponding second number in R3 is 3. So in place of R3, we'll put 3. And in place of R1, we'll put minus 1. So it will become 3 minus 1, which is equal to 4. So we'll put 4 here, and in the third position we have 1 in R3 and 3 in R1, so it will become 1 minus 3. So 1 minus 3, which is equal to minus 2. So we'll write here minus 2. And in the final step, the last number here is 5 in R3. So 5, R3 is 5, and R1 is also 5. The corresponding R1 is 5. So it will become 5 minus 5, which is equal to 0. So we get this number. So our objective is to convert these three numbers into 0. So we start with the first column, and then we'll move to the second column and then convert this 4 into 0 by using this position as our pivot. Okay, so in the first step we convert these numbers into 0, which we have achieved here. And if you follow the rules of the transformation as I've explained here, you won't have any confusion, and you won't end up in a situation where you converted a number to 0 in the previous step, and in the next step this again becomes non-zero, and then you'll have to again convert it. So it will be like a never-ending loop. You try to change one number, that affects another number, and then you want to change that. So to avoid all of that, follow the rules, and you will be saving yourself a lot of time and a lot of confusion. Okay, so now the first step, we have converted the first the bottom two numbers of the first column into 0. So what is remaining is to convert this number into 0 using this position, the position which I marked in green as our pivot. So that would be our step 2. And once we have done that step, we would have converted the augmented matrix into the row echelon form matrix. So let's go into that step and complete that as well. So that would be our step number 2. So in this step we are going to use this position as our pivot, and using that as the pivot we are going to convert this position into 0. Once we have done that, all the numbers below the diagonal of the coefficient matrix would become equal to 0, which is our row echelon form. So because we want to convert this number which is in row 3 to 0, so we have to apply some transformation to row 3 now. So the transformation has to be applied to all the numbers of row 3, and the transformation rule is the same. We are going to change row 3 now. So we'll write row 3 transforms to row 3, that's R3 minus the value that we want to change to 0 is 4 here. So we'll write that 4 divided by the pivot value. So the pivot value here is 6. So if you just remember that the pivot is always on the diagonal. So when we are operating on the first column, that's our pivot. When we are operating on the second column, the pivot moves diagonally downwards. So the pivot here is 6. So we have 4 by 6. And where is the pivot? The pivot is in row 2. So we will multiply this with row 2. So that's the transformation that we are going to apply to our matrix in this step number 2 to convert this position value into 0. And we'll apply it to the entire of row 3. So we can simplify this transformation as R3 transforms to R3. We can write it as 2 by 3 or leave it as 4 by 6. That's not a problem. I'm just going to leave it as 4 by 6. Either way you'll get the same answer. 4 by 6 R2. So the first number that you have in R3 is 0. So in place of R3 you'll put this number 0. So 0 minus 4 by 6 into R2, and the corresponding number in R2 is also 0 into 0. So that gives us 0. So in this step we are making changes only in row 3. That means row 1 and 2 are going to be the same. So we'll write down rows 1 and 2 as they are. 1 minus 1 3 5 0, 6, minus 13, minus 20. And we are applying a transformation to row 3. When we apply it to the first element, it remains as 0. That's what I meant. You make the calculation in such a way, the transformation in such a way that the 0 that you converted in the previous step, you don't want to alter it and make it as non-zero when you're changing this, right? If this became non-zero in your calculation, then you'll have to do one more step to make the 0 again. Okay, and that could alter some other number and so on. So to avoid it, just follow the rules of the transformation as explained in this section. Okay. Next we move on to the second number, which is 4. So in place of R3 we are going to put this 4, and in place of R2 we are going to put the 6. So the second number is 4 minus 4 by 6 into 6. So the 6 and 6 will cancel. So 4 minus 4 is 0, which is what we want to do. So we got the 0. Next we insert in place of R3 this number minus 2, and in place of R2 we'll put minus 13. So we want to do it element by element as we move from left to right. Okay, so in place of R3 it will be minus 2 minus 4 by 6, and what is the number in R2? The corresponding number in R2 is minus 13. So we just need to simplify this. So that will become minus 2 minus of minus will become plus 52 by 6. So we'll take the LCM as 6, and this 1 6 is 6 into minus 2 will be minus 12 plus 52, which is equal to 40 divided by 6. So we get the number here as 40 by 6, and in the last element R3 is 0. So in place of R3 we'll put 0, and in place of R2 we'll put minus 20. So that will be 0 minus 4 by 6 into minus 20. So that will give us minus into minus will become plus. So that will be 20 into 4 is 80 over 6. So the number we get here is 80 over 6. Okay, so obviously when you're doing the transformations, you might get fractional numbers as well. You can leave it as a fraction or you can represent that as a decimal. Either way, it should give you the same answer. So if you notice here, what we have achieved is we have made all the numbers below this diagonal as 0. So that is our row echelon form of the augmented matrix. So we have transformed the augmented matrix into the row echelon form. Okay, so these are the row operations we perform to convert the augmented matrix into the row echelon form. And once we have this row echelon form of the matrix, we move on to the final step, which is called as the back substitution step. So the back substitution step will give us the solution. So once we are in this step, if you recall, the matrix is the augmented matrix is having the coefficients of x, y, and z in these positions, right? So the augmented matrix had the first part, which was the coefficient matrix, which was just having the coefficients of x, y, and z in each of the columns. What we did basically here in the Gaussian elimination process is that we eliminated the coefficient of x from the second equation, and we eliminated the coefficient of x as well as y in the third equation. So if you notice here, in the third equation we have an equation which is in the third row we have an equation containing only one variable, which is z. So it is 40 by 6, z is equal to 80 by 6. So we can solve for z. Then in the second equation, or the second row of this row echelon matrix, we have eliminated x. We have only two variables, y and z. and because we have already obtained the value of z from this third row, we can substitute that value of z and solve for y, and then we can substitute the y and z in the first equation to get the value of x. So that's a process called as back substitution. So by using back substitution, we can now first solve for z. So 40 by 6 z is equal to 80 by 6. So that means we can multiply both sides by 6. 40z is equal to 80. So that corresponds to z equals 2. And if you recall, for these equations, when we solved it previously using the matrix inversion method as well as the Cramer's rule, we got the answer as x equal to 0, y equal to 1, and z equal to 2. So we've got the z equal to 2 here. Now we will substitute this value of z in the second equation, which contains y and z, and solve for y. So the next step would be to solve for y. So we'll solve for y using the second row of the row echelon matrix. So the second row gives us 6y minus 13z equals minus 20. So that means 6y minus 13 into z. The value of z we have obtained here as 2, so we can substitute that over here. So that's why we call this as back substitution. So 13 into 2 equals minus 20. So 6y minus 26 equal to minus 20. We can take this minus 26 to the other side of the equal to. So 6y equals minus 20 plus 26, which is equal to 6. So therefore y is equal to 1. And again, that's the answer we got previously as well. Now we will substitute both these values of y and z into the first equation, which is x minus y plus 3z equals 5. We know the values of y and z now, so we can solve for x. So x minus y is equal to 1 plus 3 times z is equal to 2. That gives us 5. So x minus 1 plus 6 is equal to 5. So minus 1 plus 6 is plus 5, yani x plus 5 equal to 5. That corresponds to x equals 5 minus 5, which is equal to 0. So we get x equal to 0, and that is exactly the same solution we had previously as well. So by using this Gaussian elimination, we have again solved these equations and obtained the values of the variables x, y, and z, which corresponds to the point of intersection of these planes in the space. Okay, now again, I want to quickly recall what I said in the previous section as well. Once we convert this into row echelon form, we can end up in 3 different situations. The first is a situation where this lower triangular elements are 0, and so these are 0, and we have some numbers in this position and this position, so we can solve this. So this gives us a situation where we have a unique solution. It could be that the entire of the third row or any of the rows, okay, maybe even the second row, if one of the rows becomes all zeros in trying to implement the performing the row operations according to the rules we have described just now, if an entire row becomes 0, that will correspond to a case where there are multiple solutions or infinite possible solutions. So for example, it could be that in the entire of row 3 becomes 0, 0, 0, 0, or the entire of row 2 becomes 0, 0, 0, 0. In that case, we that's an indication that this that particular system of equations has multiple solutions. Similarly, if we end up in a situation where we have the coefficient elements or the coefficient numbers 0 and the constant number here as a non-zero number, so that means 0x plus 0y plus 0z is equal to some number. That's not possible. That's an impossible equation, right? So if you get, for example, this has 0 and this is non-zero, then that corresponds to a case where there is no solution at all. That means those lines or planes do not intersect anywhere at all. But if any row becomes all zeros, that is an indication that the system of equations has multiple or infinite possible solutions. Okay, we will discuss both those cases also in the next part of the video. So the set of equations or the system that we have solved here is the case where it gives us a unique solution, in the sense that if we take the original matrix, which is the coefficient matrix here, and the A matrix, that is, and if we take its determinant value will not be equal to 0, right? That means it gives us a unique solution. So the case that we have discussed over here, we'll call it as the case 1, which gives us unique solution. So this is case 1. It gives us a unique solution, and that happens when the determinant value of the coefficient matrix is not equal to 0. Okay, and you can verify that for the given set of equations. If you take the coefficient matrix or the A matrix and compute its determinant, you will find that it is not equal to 0. Let us now look at the second case, where we'll choose a system of equations where it gives us multiple solutions. Whether it is multiple solutions or no solution, the determinant value will be 0. So let's look at the second case, where we will see that the system has multiple solutions, and we will see what happens in that case. We'll notice that one of the rows, after the conversion to row-echelon form, an entire row may become completely 0. So that would give us an indication that this system of equations has multiple possible solutions. Okay, so let's work out on that. We will now apply Gaussian elimination to a system of equations which represent a situation where the system has multiple possible solutions. And once we solve it, and you will see in the final stage of at the end of the Gaussian elimination process, we will show what form this matrix takes. That will give us some indication that this particular system has multiple possible solutions. Okay, and another point that I would like to highlight here is that this is a system of equations which represents a homogeneous system. And if you recall from the definition of homogeneous system in the previous video, a homogeneous system is one in which the vector b, that is the right hand side of the equations, have all zeros. And in such a case, for a homogeneous system, it does have a trivial solution as one of the solutions, which is the origin. So x equal to 0, y equal to 0, and z equal to 0 is definitely one of the solutions. But other than that, it also has multiple possible solutions, and in this particular case it in fact has infinite possible solutions. Okay, so this is a system or a set of equations that represents a homogeneous system, because the b vector is having all elements which are equal to 0. And we will now apply Gaussian elimination to this set of equations and see what the form, the final matrix or the row-echelon form matrix takes, and what can we infer from the final row-echelon form of the matrix. So the first thing we are going to do is we are going to transform these two numbers in the first column into 0 by using this as our pivot. So we'll apply some transformation to row 2 and another transformation to row 3 using this as the pivot. So the first row is going to remain unchanged, so we'll write the first row as it is. So that will be 2 4 1 0. The second row is going to get transformed by some row operation as we described earlier. So R2 is going to get transformed as R2 minus the whatever value that we want to make to 0. So we are applying it to row 2. So whatever is the number present here, in this case it's minus 1. So we'll write that minus 1 divided by the pivot value. So here the pivot value is 2. So we'll write that 2 here. And where is the pivot? The pivot is in row 1. So we'll multiply this thing by R1. So the transformation becomes R2 transforms to R2 minus into minus is plus. So plus 1 by 2 R1. So that's our transformation that we are going to apply to row 2, and we have to do it element by element for each of the numbers in row 2. So we'll start with the first element. So we'll replace R2 with minus 1 and R1 with 2. Then in place of R2 we'll put 1, and in place of R1 we'll put 4. And in the next step, for the third number, this R2 we'll put minus 2, and R1 we'll put this 1. And for the last numbers, it's 0 and 0 for both R2 and R1. So we will apply that, and we will see what is the transformation or the transformed values we get for row 2. So the first element is minus 1 plus 1 by 2, and the position in row 1 is 2. So the 2 and 2 will cancel, so minus 1 plus 1, we get it as 0. So we get here 0. And similarly, the next number in R2 is 1, and the next number in the corresponding R1 is 4. So that will become 1 plus 1 by 2, and the number in R1 is 4. So 2 will go here 2 times. So 1 plus 2 will get this as 3. So the second number here becomes 3. And the third number will become minus 2 plus 1 by 2 into 1. So minus 2 plus 1 by 2, that's minus 2 plus half is minus 1.5, yani minus 3 by 2. You can work out that calculation. So that becomes minus 3 upon 2. And the last number would be 0 minus 1 by 2 into 0. That will obviously give us 0, so that remains unaltered. So we have converted this position into 0. Okay, and whatever transformation we are applying to this number, the same transformation has to be applied to the entire row. Okay, next we want to convert this 4 to 0 using this 2 as our pivot. So we'll apply some transformation to row 3. So our row 3 will transform to R3 minus whatever number is present in that position. So in this case it's 4, so we'll write that 4 divided by the pivot value is 2, so we'll put that 2, and the pivot is in R1. So that is equal to R3 minus 2 R1. 4 by 2 is 2. So the transformation we get is R3 minus 2 R1, and we will apply that transformation to each of the numbers. So in place of R3 we'll put 4, and in place of R1 we'll put 2. And for the second number, R3 will become 0, R2 will become 4, R1 will become 4. And the third number, R3 will become 6, R1 will become 1, and so on. So we'll substitute each of these numbers and get our transformed values for row 3. So it will become 4 minus 2 times R1 is 2, so that's 4 minus 4, we'll get it as 0. The second number will be 0 minus 2 times 4. That will give us minus 8. So we have 0, we have minus 8. And the third number will be 6 minus 2 times 1. So that will give us 4. And lastly we have 0 minus 2 times 0, which is still 0. So we get this as 0. So now we have applied the first step of the Gaussian elimination process, whereby we have converted these two numbers into zeros. So we are interested in converting this lower triangle as zeros. So you achieve the first step. Now we will convert, in the second step, we will convert this minus 8 to 0 using this 3 as a pivot, because the pivot lies on the diagonal of the A matrix. So in the first step, this was our pivot. Now when converting this minus 8 to 0, this element would become our pivot. So we will use this as a pivot and write the transformation operation or equation to convert this to 0 and apply that same transformation to the entire row 3. Now what we want to do is to convert this to 0 using our pivot as this position. So the pivot is going to lie on the diagonal elements, right? So this is our pivot, and using this as our pivot, we will convert this to 0. And this minus 8 here is in row 3, so we have to apply a transformation to row 3. So in this step, row 1 and row 2 are going to remain unaltered. So we will rewrite rows 1 and 2 as they are. So 2, let me write that in a different color. So that's 2, 4, 1, 0. The second row also remains unaltered, so that will be as it is: 0, 3, minus 3 by 2 and 0. And we'll have to apply some transformation to row 3. So the rule for the transformation would be R3 transforms to R3 minus, that's the value that we are interested in changing to 0. So the value there is minus 8. So we'll write that minus 8 divided by the pivot value. So the pivot value here is 3. So divided by 3. And where is the pivot value? The pivot value in this case now is in row 2. So we'll multiply it with the row 2 numbers. So R2. So we can simplify that as R3 transforms to R3, minus into minus will become plus 8 by 3 R2. So that's the transformation we are going to apply to all the elements of row 3. So for the first position, it will be R3 will be 0 and R2 corresponding R2, R3, R2, R3, R2, R3, R2, R3, R2. We are going to substitute these element by element and find the new values for R3. So the first number will be 0 plus 8 by 3 into 0, which is equal to 0. The second one will be minus 8 plus 8 by 3, and the corresponding R2 is 3. So 3 and 3 will cancel. So minus 8 plus 8 is 0. So we get this also as 0. The next number is 4 in R3 and minus 3 by 2 in place of R2. So we'll have it as 4 plus 8 by 3 into minus 3 by 2. So that will give us 2 will go here 4 times, 3 and 3 will cancel, and we have the minus here. So this effectively 4 into minus 1 is minus 4. So 4 minus 4 is 0. So we have this as 0 as well. And the last number is 0 plus 8 by 3. So it's the 0 plus 8 by 3 into 0, which is equal to 0. So you see here, in this case, we have got an entire row consisting of zeros. So this is an indication that the system of equations has multiple solutions or infinite possible solutions. So we can't directly solve from here, okay? We have to stop here and we'll use some other method to find the solution, and that is we can fix a particular value of z, and for corresponding to that value of z we can find what is y and x, or we can choose any other value of z, and then for that value of z we can try to find out what is the value of x and y and so on. But when we convert the augmented matrix into the row echelon form matrix, you see here that this is the row echelon form. We got these zeros, but it has also caused, the application of Gaussian elimination has also caused an entire row to become zero. So you see here that an entire row has become zero at the end of Gaussian elimination, at the end of Gaussian elimination. Okay, so this means that if you get this particular situation, it means that this system of equations has multiple possible solutions. So this system of equations has multiple possible solutions. Okay, and if you check the determinant of the coefficient matrix for these set of equations, you will notice that it gives you a determinant value equal to 0, but just by looking at the determinant value you cannot conclusively say that the system has no solution or multiple solutions. Now that information can be obtained by applying Gaussian elimination and getting the matrix into the row echelon form. And in the row echelon form, if you notice that an entire row has become zeros, then it means that the system of equations has multiple possible solutions. Okay, and in the next video we will discuss about the third case where the determinant is equal to 0 and the system of equations has no unique solution at all. In that case, what happens at the end of the Gaussian elimination process, or what will be the resultant matrix at the end of the Gaussian elimination process? What you will see that is you will get these as zeros, but here you'll have one of them as 0 and the other one as non-zero. So this is 0 and this is non-zero. That's like an impossible solution or impossible situation, which says 0x plus 0y plus 0z equal to some number which is non-zero. So that is an impossible situation. So that would indicate that the system has no equations. We will do that example in the next video. Now another important point that I want to highlight here in this set is that, or in this section, is that what are the acceptable transformations or operations that can be applied to the row operations. The row operations can have, you can add two rows, or you can have the addition or subtraction of two rows. You can multiply a row with a constant, and add to another row. Now if you notice in these transformations, we are multiplying R2 with a constant and adding it to another row, right? So even in the previous thing here, we are multiplying a row with some constant and adding it to another row. So we can add or subtract two rows we can multiply a row with a constant and add it to another row, or we can simply multiply a row with a constant. That's all allowed. But what is not allowed, it would be a big mistake if you do that, okay? Not allowed or not valid transformations. You cannot add or subtract a constant to or from a row. That means if you write it as R2 becomes R2 minus 5, that means you are subtracting 5 from R2, wrong. Or if you write R3 becomes R3 plus 8, this is wrong. This is a big mistake, okay? These row operations are not allowed. You can multiply a constant to a row, and then after multiplying a constant to the row, you can also add that product to another row, or you can add or subtract two different rows. You can write it as, for example, R1 plus R2 is allowed, or R2, or you can say, for example, R1 becomes R1 plus R2, or you can write R2 becomes R2 minus R1 masalan, okay? So all of this is acceptable. Or you can say R2 becomes R2 minus some constant C times R1. So we are multiplying a constant to a row and adding it to another row. Or we can also write, say, R2 becomes R2 plus C times R1. So these are all acceptable transformations. But if you add or subtract a constant to a row, that is an absolute error, okay? It is absurd. Doing such a transformation is totally absurd. It is incorrect, and it would straight away result in an incorrect solution. So do not ever try to add or subtract constants to the rows like this, okay? So make sure that you follow the operations properly. But if you stick to the procedures that have been described earlier, it would keep you in the right track. Okay, we'll continue in the next section and in the next video, where we'll use Gaussian elimination to a system of equations which represents a system that has no solution. That means there is no point of intersection. So we will solve that and see what form the matrix takes at the end of the Gaussian elimination process, and how would we infer from that resulting matrix that that system of equations has no solutions.